In 2018, the Fleish Hydroelectric Plant suffered a failure of its 113-year-old water discharge assembly. This assembly, known as a tailrace, broke away from the plant, resulting in chaotic water discharge which threatened significant damage to the plant's power generation turbine. Because of the location of the failed tailrace, a difficult and innovative repair approach was required.
In April of 2018, we lost the north tail race in this facility. The tail races are the discharges back to the river. On this particular turbine, there's a single inlet, double discharge on this. So each of the discharges has a tail race that discharges water back to the river, the return point. The tail race fell off and was retrieved and pulled back over to our Fleish lumberyard. And from there it was reverse engineered. So we brought in an engineer and they measured and did a survey down in the down at the discharge point, and like I said, reverse engineered the whole thing here. So this project presented probably one of the most challenging projects I've ever worked on, as far as the work was all done for the most part underwater. The original tail races were riveted steel pipe. A piece of junk only lasted 100 years. So once it tore loose from the foundation, we had to devise a means to connect the new tail races to the building foundation. So we design came up with a flange, big flange on each tail race, and once the design was completed here, we had to evaluate the condition of the foundation there. We found at the point the river was up high, we knew that there was some voids underneath the tail races. To the extent that we couldn't determine. We did some cameras that were underwater, and the clarity of the water didn't allow for as much exploration as we had hoped for. When we were doing the construction, we had found that there were some great big voids underneath into the foundation to the extent of about 4 feet. We found on the draft tubes, or the interface between the draft tube and the tail race, that connection there. On the draft tubes themselves, there was some holidays that had developed in that steel pipe, and there was water jetting that had taken the foundation out and eroded that foundation away very badly. That created those 4-foot voids that were back in there. One day as I said, all this work was done underwater, so we had a diver in the water, and there was he was reaching back into one of the voids to check something, and about a 3-foot beaver swam out from there. He had to come up and change his diver suit. So anyway, we had to, all of this work being done underwater, we had to build a shelf to support a form. We had to build the form. We ended up pressure grouting. The voids took nearly 4 pallets of grout. With the grout in place, we had to drill an epoxy in, I think it was 76 stainless steel dowels to hold these tail races on place onto the flange, with the flanges in place. There was a lot of kind of unique solutions that we had to come up with for the way that this project was done, and because of the fact that it was underwater. We ended up, because the clarity of the water was so low, the turbidity was high, we couldn't see much more than about a foot in front of the diver's face there. The diver came out of the water one day. He says, "Put on a pair of ski gloves, put another pair of gloves on it, blindfold yourself, jump in a pool of water, and try to tie a zip tie." He said that's pretty much what you're working with out there. So one day, first day we came out here, he's swimming under ice. So they were working in dry suits, and the working conditions were very, very hard, very tough. Anyway, getting back to the construction of it, with the voids pressure grouted, having to put the flanges on place required installing dowels, and to get these dowels right with the high turbidity, we had to come up with a means so that the diver didn't have to worry about how he was drilling. All we wanted to do was drill a hole. We had 76 of these dowels to put in. Each dowel, with the exception of a few on top, were 20 inches long. So we came up with a steel template that we mounted on the over the draft tube, and then we devised a jig with a magnetic base that we could attach to the template. It was self-centering in the template hole to allow the diver to drill the holes in a straight fashion here. So he didn't have to worry about if he wasn't being perpendicular to the face or the plate. He could all he had to worry about was drill and brace himself to drill those. Again, all underwater. So once those dowels were drilled, each dowel was epoxied into place. Then he had to make sure it was perpendicular. As it was, we ended up taking the flanges back and oversizing them, tail races back and oversizing the holes so that we wouldn't have any issues with when we're flying these things in. We also made some guide dowels to where we had the 20-inch dowels and then some guide pins to capture the flange and help guide those and bring those into place, because being these were stainless steel, just one little mistake and we'd dowel it or gall one of the dowels and we wouldn't be able to wouldn't be able to get a nut and pull it down tight. So a lot of thought had to go into how we were going to do this. So the contractor brought in a 110-ton crane on installation day, and we picked each tail race up. It was on a spreader bar, had about a 3,000-pound counterweight on the outside of it. Flew it out there, and we got it near in place. The guide pins picked up the flange, and everything slid in pretty nicely. Didn't have any issues with alignment or anything. Got the nuts onto the threaded dowels and pulled everything tight. So we're noticing a much better vacuum on the draft tubes than we had previously. So this facility runs on single inlet, double outlet. The two draft tubes, the draft tubes actually draw a vacuum. And when the tail race was lost off of the north side, there was an imbalance across the machine, and so the machine tended to thrust to the north side, and that put a lot of forces on the thrust bearing. And we were seeing that, and there was a lot of heat buildup in the thrust bearing, so it's important that we have those draft tubes. So since doing that, now that we have this project completed and we're back online, there's a good balance across the machine. We have nearly equal vacuum on either side of the draft tube, so everything seems to be working pretty good.